Hi and Assalamualaikum. My name is Ahmad Abra bin Ayub and we are from Group 15. So our title is Partial Differential Equations and this is our team assignment too. Our members consist of three persons which is Muhammad Fahan bin Waziri, Ahmad Abra bin Ayub and Gua Chiki.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Farhan bin Rozili. My matrix number is 208240. So, for the first part of the team assignment 2, I will present the objective part. The objective of this team assignment 2 is to find the uses of the partial differential equation in many aspects. This is because the partial differential equation can be applied in any field of study. In general, physical and other issues involving functioning of variables such as of the heat and or sound propagation, fluid flow, elasticity, electronic and others can be solved by using the partial differential equation. Next, to investigate the application of the partial differential equation in specific field of the study. Besides, the objective is also to learn about the uses of partial differential equation in wave equation, heat equation, and Laplace equation. So, lastly, the objective is to explain the principle of partial differential equation on specific with equation, heat equation, and Laplace equation. The detail of the explanation could improve the level of understanding of the student. So that's all.
And I, as Ahmad Abra bin Ayub, with matrix number of 208001, will present. So the introduction of partial differential equations that the partial differential equations PDE is a mathematical equation that establishes relationship between the partial derivative of the multivariable function in an algebraic equation like x squared minus 3x plus 2 equal to 0. The function is commonly thought as an unknown to be solved for similar to how x is thought of as an unknown quantity to be solved for. However, implicit formula for partial differential equation solutions are frequently impossible to write down. As a, as a result, there's a lot of recent mathematics and scientific study on how to use computer to numerically approximate solution to a partial differential equations. The identification of a general qualitative features of a solution to a various partial differential equations is also large area to a pure mathematical research, where the usual questions are broadly speaking, on the identification of general qualitative features of solution to a various partial differential equations. So the differential equations is the with the curly d is that dv over dt with curly d, as we can see in our next slide. On say that the function of u, x, y, z of the three variables is a harmonic or a solution of the Laplace equation is to satisfy the condition. So here we have the u equal to 1 over uh, square root x squared minus 2x plus y squared plus z squared plus 1 equal to 2x squared. And when we do the math, the u is equal to sine xy plus z. So it's perhaps surprising that the two offered instances of a harmonic function are so unlike. This is due to the fact that they are not, in any way, both partial instances of a Laplace equation general solution formula, which is curly d squared over y over curly dx curly dy equal to 0. So here the difference between the partial differentials with the normal differential equations. That the normal differentials is equal to dy over dx, but while the partial differential using curly t So as we can see here, that the formula at the lower of our slide, it is second order derivative, which is partial differential. You can see that d squared y, or I can say curly d squared y over curly dx and curly dy. Here, first we differentiate against x, and second we differentiate against y. But both of it is the equation of it is both y equal to something something something. Yeah?
Okay, now I will present to you about the principle of the heat equation for the team assignment 2. So firstly, we would like to solve the heat equation, which is you can see on the first right formula, which is a ut minus qux equals to 0. So this principle of heat equation can be solved by using the D'Alembert solution. D'Alembert solution is usually used to solve the wave of IVP because they do not provide anything for the heat equation. And we have to also remember that the heat equation is one of the parabolic type, which is mean that has one type of characteristic line. So if we rewrite the equation, we will get like on the following second formula, which is quxx plus dot equals to 0. So the dot is represent the lower order terms. The coefficient of the leading order term can be seen as a equals to k, b equals to c equals to 0. So next, we have to calculate the slope. Lastly, we have to calculate the slope of the characteristic line, which is like it shows on the left of the last formula. So because we use the partial differential equation because of the technique that we learn to reduce the heat equation to an ordinary differential equation. So it become more easily to solve by using the partial differential equation. So that's all from me. Thank you.
So let's talk about the application of the Laplace equation in the mechanical engineering. In the field of mechanical engineering, the Laplace transform is commonly used to solve differential equations that rise during a mathematical modeling of the mechanical system in order to determine the system transfer function. So let's do the example of the Laplace equation in mechanical engineering. So here, for example, we have the tank shown in the figure is an infinite empty, which is t equal to 0, which is the starting time. A constant rate of flowing, which is qi, is added for t is bigger than 0. The rate at which flow leaves the tank is the cross-sectional area of the tank is q naught equal to ch. Determine the differential equations for the heat h. Identify the time constant and find the transfer function of system. So at the right side of the slide, we have the figure below, the figure. So here given that Q naught equal to 0, M equal to mass of fluid, E equal to density of the fluid, and M equal to, which is mass equal to volume plus density, which is our basic formula, and it's also equal to AH times E. So let's do the math, which is AH times E, when mass flow rate equal to M equal to dm over dt, uh, which is when we differentiate m against t, we will get dm over dt, and d over dt is equal to ah times e equal to ea times dh over dt, because we just expand it, and we know that mass of flow rate into the tank equal to mass in flow rate minus mass out flow rate, and we take the equation above, dA times dH over dt equal to E QI minus E Q naught. Then A to the times dh over dt equals to qi minus q naught. A times dh over dt equal to qi minus ch, then qi equal to a dh over dt plus ch. This equation represents the differential equation for heat m, taking Laplace transform on both sides. So here we have the uh, last formula for our last solution for our example just now, which is L equal to A L times with the dH over dt plus CL times H. And here we got the final using the equation, we will get Q naught over Qi is equal to 1 over 1 minus AS over C times S. So the equation represents the transfer function of the system, which is tau equal to A over S. So that is for me. Let's move to the other person.
So now I will present for the parts of the application of the heat equation, which is the maximum principle for the team assignment 2. The the application I choose is to calculate the maximum principle. The maximum principle state that the maximum of the u in the bracket of x and t on each of the three sides must match the maximum of the u on the entire rectangle. The maximum principle can be represented as shows as it shows. Next, you can reduce it to the first formula you can see on the below. So when you consider to heat conduction in a thin rod, the maximum principle makes sense since the beginning temperature as well as the temperature at the end point will dissipate by the heat conduction, and the temperature will never climb over the highest starting or the end point temperature. In the reality, a stronger version of the maximum principle stating the maximum over the rectangle R cannot be obtained at the end at the point not belonging to unless the u is constant. So you can see like on the second formula, it shows on the second formula. So as the result of it, the minimum point of the function u will perfectly correspond with the maximum point, of which is there must be the u according to the maximum principle. So that's it from me. Thank you.
Hello, my name is Guo Jiaqing. The metric number is 208938. For partial differential equation, my topic is wave equation. This is contents. The part 1 is for principle and part 2 is application. Okay, for part 1, principle. The wave equation is a second order partial differential equation. It can be written like this, where C is the fixed non-negative value coefficient, and this is the C nebula operator, and this form the equation can be rewritten like this. Okay, next, the wave equation in 3 dimensions. First, in 1 dimension, the wave equation can be written as follow. This equation, and then the in 2 dimensions, wave equation is this. Can solve this problem, use the 3 dimension theory. Okay. In 3 dimensions, for spherical waves, the wave equations can be solved using technique of separation of variables. The first Fourier transform, the wave equations is like this, and then k equal omega over the c. The complete solution now given by this. For general solution, the algebraic approach, the formula is this. Okay, next. For part 2, the application. For application, it is wave propagation under a moving load. Look at the figure 1, the moving loads across a taut wire. There are 3 basic assumptions. The basic equation we use is a wave equation with the forcing term from the moving loads like this. We can use the simplest assumption of the delta functions, the step functions, and the Laplace transform method. We can get 2 solutions to this problem. The figure 2 is the solution of the moving loads problem for x equal 1/2 I and r lambda equal 0.3. And the figure 3, the solution of moving load problem for x equal 1/2 I and lambda equals 3. Okay, for conclusion, we have shown about the principle of partial differential equations and their applications in wave equation, heat equation, and transverse vibration. Partial differential equations play a major role in application of science and engineering. They are ubiquitous in mathematically oriented scientific fields such as physics. Using partial differential equations can be better solve the equation in wide variety of engineering. That's all. Thanks for watching.